Another example of frequency domain filter is shown here. So this allows us, I'm going to show that frequency domain filtering allows us to estimate subpixel shifts of images accurately. So assume we have two images, one is translated or shifted with respect to another. Of course, we can find out that shift by doing a cross correlation. But the result, we look for a peak in the cross correlation score that tells us the shift, but that is at some integer location. So we may want to find the value of the shift to some subpixel location. So we'll use this method of phase correlation in the frequency domain. This is an example of a video. It's a intravascular ultrasound image of a coronary artery. So the ultrasound transducer is here. It's actually wiggling around inside the artery as it's being pulled through. But it appears centered, whereas the artery is moving around. What we really like is to have the artery be stationary, more or less stationary, and the ultrasound transducer allowed to move. So we want to find these shifts. Okay, so the way we're going to do this is to use the translation property of the Fourier transform. So recall that a translation in the spatial domain results in a phase change in the frequency domain by this amount here. So assume that we have two images. One is shifted with respect to the other by x0, y0. That means that the new transform is equal to the old transform, but where every point uv is multiplied by this exponential here. If we take the point-by-point ratio of the new transform over the old transform, we just get these phase shifts here. So taking those complex numbers as a result of doing that division and extracting the angle, we get this quantity right here. So this quantity depends on u and v, and the values multiplied are the desired shifts that we want to find out. So this actually looks like a plane in uv space. So if we take uv, take the phase shift in radians, and fit a plane to that, which we can do pretty accurately, we can find these values of x0 and y0. So let's do an example, synthetic example. We'll take this image and shift it by some subpixel amount, take the ratio of the Fourier transforms, find the phase at each point, and plot it to calculate the shift. The way we'll shift the image is applying a affine transformation of this form. Recall that if we put ones and zeros in this upper 2 by 2, then this this lower row here is the amount that we're translating. And we'll use bilinear interpolation to create a subpixel shift. So this is what the program will look like. Let me go ahead and get, I'm going to read in let's go ahead and run that. So I've read in the cameraman image, should be called I1. I've created this Fourier transform called F1. I've created a transform. You can see T-form here is a structure in Matlab that contains the affine transformation. And this is what it looks like. So I've defined a horizontal shift of 2.5 pixels and 0 in the y. Okay, so now I'll use MATLAB's IM transform function to create I2. And I2 actually looks very similar to I1, but you can see it's shifted a little bit here. I'll take the Fourier transform of I2, take the ratio, call that F3, and then I'll find the angle at every point. I'll call that phase angle. So this is the angle at every point. I'll just show that just so we can see what that looks like. It's the angle in radians at every point. So what we want to do now is find the slope of this horizontally, because I just had a shift horizontally in this case. I won't fit a plane to it. I'll just sort of observe it. And I'll use a plot here. So I'll say plot phase angle. And let's say just for the first 50 columns. So what we're seeing here is just the first 50 columns of this, and you can see the slope has this negative value. Looks like it's about -3 over 50 is the slope. So the slope is 2 pi x0 over m. So that means if I solve for x0, it's the slope times m over 2 pi. So if I go ahead and solve for that, slope I said was -3 over 50. So slope dot m, or multiplied by m, m is the size of this image, which is 256 by 256, divided by 2 times pi. So that gives us a slope of -2.4446, which is pretty close to my my actual shift that I provided, which was 2.5. In summary, the convolution theorem says that convolution in one domain, for example the spatial domain, is equivalent to point-by-point multiplication in the other domain, for example frequency. It gives us a way to understand the behavior of filters. Examples of some kinds of filters: an ideal low-pass filter passes all frequencies with magnitudes below a specific level and attenuates all frequencies above that level. An ideal high-pass filter does the opposite. A notch filter rejects or passes frequencies at a specific point, namely the notch. What would a bandpass filter look like in the frequency domain?